Hey everybody, today we're going to talk about linear regression using gradient descent. My name is Paul Swenson and I'm a master's student at Southern Methodist University. So I want to talk about what you need to know before we get too deep into what gradient descent is for linear regression. So some things that might be helpful before watching this video are going to be linear algebra, specifically matrix math. You're also going to want to know calculus, partial derivatives, chain rule, summations, and finding local minimums and maximums. And it might also be helpful to have a background in statistics, in regression, and ways that you can measure error in your models. Some key terms that might help are going to be loss function. This is also called the cost function, the objective function, and sometimes in math notation you'll see it denoted as J of W. And this is just the function that we're going to use to measure the model error. So some that you might be familiar with are mean squared error and mean absolute error. We're also going to talk about an optimizer, and that's just the algorithm that minimizes the loss function. In this case, we're using gradient descent as the optimizer. We also have a learning rate, and the learning rate is going to be the speed at which the optimizer minimizes the loss function, and we'll talk about how that minimization happens here in a second. Higher learning rates mean faster runtimes, and lower learning rates mean slower runtimes, but it also increases the likelihood that you will find the global or the local minimum for your loss function. So here's just a quick overview of what linear regression looks like. I have the regression equation there at the top. Y is equal to the slope times x plus the intercept. So you'll see I have the intercept and the slope kind of labeled in here. And then I also have the error marked. The error is just going to be the distance from the predicted data point using linear regression from the actual data point. So here, for a given x, we see that there is a little bit of an error between the predicted and the actual values. Now, what gradient descent is going to try to do is minimize those errors within the regression equation for all data points. So, what is gradient descent? Gradient descent is the method by which we calculate the slope and the intercept for the linear regression equation by traversing the gradient of the loss function. What does all that mean? Well, here on the y-axis we have the cost function, aka the loss function, and that line is representing the error that your model generates. So what we do is we're going to pick just a random starting weight. That's where we see that ball on the right side. We pick a random starting weight, and then we're going to take steps. The steps are the size of the learning rate to descend the gradient of the cost function. And what we're doing is we're hoping to eventually take small steps down the gradient and reach the minimum of the cost function. Now, how do we do that? Well, there's a little bit of math behind the scenes. So first we're going to define our loss function as the mean squared error. And here I show y hat, that's the y predicted, is equal to the slope times x plus the intercept. So that is our regression equation that we're hoping to derive. And then we have the mean squared error, which is the actual y data point minus the predicted y data point squared and then averaged. So that's the mean squared error. And in order to derive the gradient for both the slope and the intercept, what we do is take the partial derivative of the mean squared error with respect to slope, and we take the partial derivative of the mean squared error with respect to the intercept as well. And what this is going to do is it's going to update those weights in our regression model to get as close to the minimum error as possible. You can use the chain rule to do these partial derivatives, and I have all the math kind of outlined here. If you want to pause the video and take a second to look through this, it'll maybe help you understand the math that's happening. Okay, next I just want to take a second and show you a quick coding sample. Alright, so here's my code. I wrote this in Jupyter Notebooks using Python. And just to give you guys an overview, here I am importing pandas, NumPy, and those are both just libraries for manipulating data and doing math on your data. And then I also have two plotting libraries that I'm using to visualize kind of what's going on, Seaborn and Matplotlib. Then I'm just going to read in the data, and I'm going to read in the data into these x and y variables so that they're a little bit easier for me to work with. This data was borrowed from a GitHub project, and the author of that GitHub project wrote a really great article on this same topic. I'll leave the link to that in the description below. So here, this is just the data. You see we have x and y. And it's just a quick scatter plot. You can see that there's some relationship. And what we're trying to do is use gradient descent to estimate that linear regression line. This is the math that we talked about before. And then inside the code, this is where the magic happens. First thing we do is we're going to set the slope and the intercept to 0. Now these can be any random value, but for now we're just setting them to 0 as the initial weights. And then we are also going to count n as the number of rows in the data. We have our learning rate is going to be set to 0.0001. I think that's a pretty typical learning rate. You can, again, change this value to either speed up or slow down how quickly your model will traverse the gradient. We also have 1,000 epochs, so this is just the number of times that we're going to update the weights in this model. Quick for loop is going to show the iterations, so we're iterating 1,000 times, and we're setting just this y predicted to the regression equation that we want to derive. This is where we add in those partial derivatives for the slope and the intercept. And then we're going to update the slope and the intercept based on the learning rate. So starting out, the slope is going to be 0, and then we're going to subtract. We're going to take the slope of 0 and subtract the learning rate times the partial derivative with those x values. And what this is going to do is it's going to make our slope closer and closer to the slope at the global minimum, or the local minimum. So we're hoping to minimize the error by doing these operations, and it'll do 1,000 iterations and then exit. So let's go ahead and do this. And you see it spits out a slope and an intercept value here, and then also gives us the regression equation for this data. Then we can take all of that and visualize what the regression line might look like. And this is a quick visualization. You should have seen a similar one to this earlier, where we have all of the orange dots are our predicted values for each of the x coordinates that are included in this data set. Okay, so this is the same code that you saw before. It's just a little bit truncated to remove any of the unnecessary visualizations that I put out. Some other improvements that can be made to gradient descent. The example I showed you was a very basic rudimentary one, just to give a fundamental understanding of what's happening behind the scenes. So some other improvements you can make are you can use batch gradient descent for multiple linear regression. So if you have more than one x attribute, what this will do is you can learn all of the weights in each loop. So earlier, whenever we had the epochs set to 1,000, what the batch gradient descent is going to do is it's going to update the weights for every x column at once. The next improvement that we could make is you can use what's called stochastic gradient descent. And what this does is instead of updating the weights on the partial derivatives using the entire x column, what stochastic gradient descent will do is it'll just take a random subset of the data to do the partial derivatives on, and then it will update the weights on just that random subset. This is a little bit trickier. It'll make your loss function bounce up and down for a while until it eventually converges, but stochastic gradient descent will make your algorithm run much faster. You can also use different loss functions in the gradient descent. So instead of mean squared error, you could use mean absolute error or some other custom loss function that might be useful. Another thing you can do is you can set random starting points, and this will let you train multiple models which might put you into a random starting position that has a more accessible local minimum that might even be lower than some other local minimum. So if you remember the graph that we had before where it was just that kind of U shape that we were trying to optimize, you can imagine some loss functions that have a whole bunch of valleys inside them. And by putting a random starting point in a different position, you might be able to achieve a global minimum versus just a local minimum for your loss. So that's all I have. I included all these references here that I used to generate this video, and I'll also include these in the description below. I think it's really helpful to use a bunch of different resources to kind of learn from. So if nothing clicked for you during this video, definitely go through and look at these other resources. I think they're very helpful.